Beyond the Hedges. I'm your host, David Mansuri, and today we're talking about climate change science and modeling with Sylvia Dee. Sylvia is an assistant professor and climate scientist at Rice University, specializing in climate change and the past, present, and future of Earth's hydrological cycle. She completed her undergraduate degree in civil and environmental engineering with certificates in geological engineering and environmental sciences at Princeton University, and her PhD at the University of Southern California. In 2024, she won a National Science Foundation Career Award, the agency's most prestigious early career honor. Sylvia's research focuses on how Earth's modes of natural variability, like El Niño and La Niña, compound with climate change to alter the characteristics of weather and climate extremes, such as flooding hazard on the Mississippi River. Her lab evaluates climate model data to understand future risks to human and natural systems. Outside of Rice, Sylvia regularly leads environmental science programming for the Girl Scouts of the USA, work for which she was recently honored with the Global Leadership Award by the Girl Scouts of New England. She's a regular contributor to media coverage on climate change, including from NPR, AccuWeather, and the Houston Chronicle. Thanks so much for being with us today, Sylvia. Really looking forward to this conversation.
Thank you so much for having me. I'm really excited to talk with you.
So to start off, Sylvia, you studied paleoclimatology for your PhD at the University of Southern California, and you've continued to conduct research in this area at Rice. And want to ask you, just to start our conversation today, to tell us about what paleoclimatology is and how you became interested in this field of work.
Great. So paleoclimatology is just the study of past climates on Earth. And so some people focus on climate going back 500 million years. Some folks only focus on climate over the last 10,000 years, for example. I tend to study climate going back about 20,000 years to the last ice age. But there's a variety of different reasons that we study past climates on Earth. One of the reasons is we want to understand sort of the range of possibilities in Earth's climate system. And we know that there have been major changes ranging from ice ages to hothouse climates that supported massive cold-blooded reptiles like dinosaurs millions of years ago. And the reason I got really interested in studying paleoclimate is that right now, of course, we're changing the Earth system so fast through human activities. And one of the ways we can deduce just how fast it's fast is by looking back into the past. And we can establish a baseline for what Earth does on its own naturally and compare that to the rate at which Earth's climate is changing now. So one of the major reasons we study paleoclimate is to contextualize current rates of climate and environmental change. And then there's a second reason to study paleoclimate, and that's that our climate models are basically built upon our observations from the 20th and the 21st centuries. And oftentimes we're faced with the problem of the fact that that data is pretty short compared to Earth's climate history. We only have about 100 or 150 years of data to validate our climate model physics against. And so looking into the past helps us create a new test for our climate model physics. Can it correctly simulate the last ice age? Can it correctly simulate the Cretaceous, for example? And so that's another reason that we study Earth's past climate, is to try to test the physics of our climate model simulations.
So this is maybe just a basic follow-up question, but how has the climate system changed over time? And I know you've written articles about how there were scientists who were studying human activity and the ways in which that activity was impacting the climate since the 1800s. And so I'm interested maybe both in how has the climate system changed over time, and also maybe how has our understanding of climate changed over time?
Sure. So if we look at a graph of Earth's temperature and carbon dioxide, say over the last 500 million years, what you'd see is that from about 500 million years ago to 100 or 60 million years ago, Earth went through periods where it was really hot. So, really, really hot climates. We have palm trees in the Arctic and crocodiles and very, very different ecosystems, very different arrangement of our continental plate boundaries, for example. So, different paleogeography. And then, right around 60 million years ago, there were some changes in Earth's climate system that caused Earth to start gradually cooling. And starting about 5 million years ago, we see this descent into colder temperatures that allowed Earth to actually support these ice age cycles. And so, for about the last million years, Earth has oscillated between ice age time and no ice age time about every 100,000 years. And then, if we go even further into the more recent past, if we look at the last 20,000 years, right, we know that that was when the last ice age occurred, and we've been warming up ever since. And so the last 10,000 years have been very stable. We've had very stable climate, very stable sea level. And then in the last 150 years, of course, we see this massive increase in temperature. And right now, the global temperatures we're seeing are analogous to temperatures that Earth hasn't experienced in over a million years. So it hasn't been this hot in a very long time. And we know a lot of what we know from archives like ice cores and trees and corals, and then also from marine sediments. So you asked how do we know what we know, and how has that changed over time? And that's a really good question, because up until about the 1970s, where we had the technology to get massive drill cores onto the Greenland and Antarctic ice sheets, and when we had the technology to get these deep ocean cores out of areas of the global ocean, we didn't have the technology to look back in time with the fidelity that we can now. So between these huge, long ice core records and these marine sediments that we have, we can reconstruct global temperature going millions of years into the past, which is really amazing.
Well, so, just to ask maybe a follow-up question on that, you've written about how scientists, even in the early 1800s, were learning about or studying how humans were impacting climate. What were they looking at? I'm just curious about what was top of mind for them as they were sort of doing some work in that space.
Yeah, great question. So, as early as you mentioned, in the 1800s, scientists were curious about how the Industrial Revolution would affect the atmosphere and planet Earth. So they were very aware that, right, their combustion of coal and oil was obviously changing the atmosphere, right? They could see the air pollution happening, but they also knew that combustion would produce CO2. And so there were some early scientists that did some very simple, beaker experiments where they showed that air with CO2 in it would retain heat better. And at the time, there are actually some very funny papers published where the scientists said, "Oh, Europe will be warmer. How wonderful if we keep burning coal." But they didn't really truly understand at the time the impact of long-term burning of fossil fuels on the climate system. And as our understanding evolved into the early 20th century, there were more and more scientists who were ringing the alarm bells. As early as 1920, 1930, you see atmospheric and weather and climate scientists starting to say, if we continue to burn fossil fuels and increase CO2 concentrations, Earth will get hotter. And even then, people were doing sort of back of the envelope calculations about how much warmer Earth might get. And some of those calculations were not too far off from what our best state of the art models show us today.
Huh, that's so interesting. So you mentioned models. I want to turn to modeling because I know this is an important part of the work that you do at your lab at Rice, the Climate and Water Lab, which I know looks at combining climate information from the past and also currently to try to improve predictions for what the climate will be in the future. And would love for you to talk about how you think about historical climate information and the way that informs what we know about the climate today and in the future, and then maybe about some of the modeling work you do and how that's informing kind of our understanding of what the future might look like.
Absolutely. So, as a community of climate scientists, of course, many of us are very focused on trying to understand what will happen in the future. We want to know what are the risks going to be, how can we adapt to those risks, what level of mitigation is needed, right? So questions like how will hurricane risk change in the next 100 years? How will extreme rainfall change in the next 100 years? And answering those questions is complicated. And we have really strong physical model simulations that we run, for example, to 2100 that sort of encapsulate our best understanding of how the climate system behaves. So, on top of that, what we really need to know, for example, is how will Earth's natural patterns of variability. So, listeners might be familiar with El Nino and La Nina events, which happen every 2 to 7 years or so. And our climate models are only as good as our observations. And right now, we only have something like 20 or 30 El Nino and La Nina events that we've seen with satellites. And furthermore, the tropical Pacific is totally massive, and it's very hard to understand exactly what's happening at every single time. And so we have these issues in earth sciences that our observations are not always complete. We can't always see the atmosphere and the ocean in every single detail that we need. And so one of the things we try to do in my lab is we try to use paleoclimate to fill in some of the gaps in our knowledge of how the tropical Pacific affects our day-to-day weather and climate and how it might affect future global warming. So if you can imagine, if you have a really strong El Nino event in the tropical Pacific gets really hot, that affects weather and climate in the United States through atmospheric waves, which change our precipitation, for example. And on top of that, we're superimposing radiative forcing from humans. So global warming is happening. The atmosphere is getting hotter. And what we don't quite know yet is how will that compound with El Nino. So if we have a strong El Nino and global warming is on top of that, how will they interact? Will there be constructive interference, right? Will we get even stronger El Nino events or stronger La Nina events? And there's really no way for us to figure out what might happen in the future to El Nino and La Nina. And the only tool we have is to look at how did they react to major global changes in the past. So we ask questions like during the last ice age, which is obviously not a warmer analog, but a colder analog, what happened to El Nino and La Nina? During 6,000 years ago, tropical Pacific, the amount of radiation we were getting from the sun was slightly different. How did El Nino events react? And that gives us some clues as to how these events might play out over our lifetimes. So essentially, we're trying to understand the connections between these big modes of Earth's natural variability, our natural patterns, and how those cascade into extreme rainfall or even hurricane risk in the United States, and then how those patterns are going to interact with global warming. So that's a bit of a long-winded answer, but we're trying to be data agnostic. We're trying to take our climate models and say, what other information can we gain from the past to inform what we might see in the future?
And I'm curious, Sylvia, a topic that has come up throughout this season's episodes, no matter what the sort of area of research or study is the ways in which AI and artificial intelligence is impacting the research that folks do. And I'm curious, I would guess that you may be using or considering using sort of AI as you look at this data. I just wonder, what does that look like in your lab? Is that something you're thinking about, working on, applying to how you do modeling in this space?
Yeah, absolutely. So we do use some AI techniques, and many in climate science. We use it for pattern recognition, for time series analysis to find patterns in our data. There are many people in climate science who are trying to, I mentioned we have these gaps in our observations. There are people who are trying to help climate models run faster to fill in some of the gaps in our physical understanding, where we have sort of parameterized models based on the best observations we have, but maybe it's clunky and slow, and maybe AI can do it faster. So there are many ways in which AI is being used in climate science. I will, if we have time, I'll tell one interesting anecdote though about how AI has not been useful. So in climate modeling, we are relying on physical relationships in the atmosphere and the ocean and their interactions. And there was a very interesting paper published a few years ago where scientists tried to replace a lot of the physical relationships in the climate model with machine learning. And in order to get a machine learning model to work, you have to train it on existing data. But if the training data set is for a period of Earth's history that Earth was colder, and we're now accelerating into a mean climate state that's 2, 3 degrees hotter, those physical relationships don't behave the same way. It's almost like you take an AI algorithm and you train it on English and you ask it to predict Spanish. So for future climate prediction, AI simply doesn't work. We have to use physics because that's the only thing that will properly capture how these relationships are changing as we increase carbon dioxide and methane in the atmosphere.
That's such a great example of both ways in which AI can be used helpfully to help us understand relationships and what data exists and model and project the future, and also the limitations, right, based on what data is used to even train these models. So yeah, thanks for sharing that. That's a great example. So you mentioned you just mentioned a bit about what we know about carbon in the environment. And again, this is a basic question, but I think just helpful. You're an expert on this topic, so I just want to ask this question. How do carbon emissions, and I'm sure everybody's heard about the impact that carbon has on the environment. How do carbon emissions impact our climate? And where are these emissions, or maybe the most significant carbon emissions, coming from? Are they coming from cars? Are they coming from cows? Where are they coming from?
Yeah, good question. So I'll answer your second question first. So carbon emissions come primarily from a few different sectors. So the biggest one is electricity production. So burning of fossil fuels to create electricity. A big one is transportation, as you mentioned. So ships, airplanes, all of those are another big chunk. Industrial agriculture and manufacturing. So that's going to be another big piece of the pie. And then, as you mentioned, methane comes, I guess, carbon from methane, right? There's a big part of industrial agriculture that results in methane emissions. So those are the main sources. If you look at sort of individuals or individual homes, it's actually a very, very small fraction compared to some of those major sectors: transportation, electricity production, industry, and agriculture. And then, so the effect of those carbon emissions is to essentially trap outgoing heat from Earth's surface. So I actually just taught my 100 level intro class today about the greenhouse effect. So as radiation is leaving Earth's surface, it is reabsorbed by CO2 and methane molecules, and it's re-emitted back to Earth's surface. So it's almost as if we have a blanket of greenhouse gases, carbon in our atmosphere that are keeping Earth warmer than it would be otherwise. And so as we increase the amount of carbon in the atmosphere, we're simply making our atmospheric blanket thicker and thicker. And we can very clearly see in observations over the last 150 years that Earth has been getting hotter and hotter. What impacts people might not think about as much is that as we warm up the atmosphere, there are cascading impacts on us that are linked to that warming. So, for example, if we take hurricanes, hurricanes are driven by warm ocean waters. So if we heat up the atmosphere, that heats up the surface ocean, and that warmer surface ocean powers stronger and more frequent hurricanes. Another example is rainfall. So the most extreme rainfall events, if we warm up the atmosphere, folks who have lived in Houston know that a hotter atmosphere can have a higher humidity. There can be more water vapor in air that's hot. We've all sat through Houston summers, and I'm sure you know that even if the humidity is high on a cold day, it doesn't feel miserable. But a warmer day, you can just have much more humid conditions. So as we're warming the global atmosphere, it can store more water vapor. And that means that the heaviest rainfall events are even heavier. So the way I teach this to my class is, if you take Hurricane Harvey, you have about 50 inches of rain that fell in certain places. So what if that storm was 30% more rain, right? So in the biggest rainfall events that we have, we're talking about a couple more feet of rainfall that could harm different places, different infrastructure, and cause disruptions to our power grid. So really, these climate changes that they seem abstract, oh, carbon in the atmosphere, but the cascading impacts of the atmospheric warming are all around us and will continue to affect us for many hundreds of years, unfortunately.
So you mentioned hurricanes. I've heard you on the radio recently talk about the fires in California and how those are connected to the changing climate, and wonder about what other sort of extreme weather events are you thinking about, watching, researching right now? I know you've done research on flooding as it relates to the Mississippi River, and I think also, as someone who is in Houston, you mentioned some examples of the kinds of more extreme weather that folks might be experiencing in Texas or in the South, and would love just for you to talk a bit about what other kinds of extreme weather events are you watching, are you researching, are sort of top of mind for you right now?
Yeah. Well, so it's funny. When I started working at Rice, I became interested in this whole new body of research about sort of Gulf Coast relevant climate change. And I realized shortly after starting to work here that Houston is really ground zero for climate change. We have every type of weather and climate disaster. We have extreme flooding. We have hurricanes. We have bad droughts that are getting worse over time. We have river flooding. We have extreme heat and heat waves. My lab has worked on some of these topics. I haven't worked as much on wildfire since that's luckily not something that we get too much of here in the Houston area. But certainly, I mentioned the relationships between atmospheric warming and extreme rainfall and flooding and hurricanes as well. And I have to say that undergraduates here at Rice have driven a lot of these research directions because I've let them lead and what they're excited about working on. So they'll learn about heat waves. They'll be here doing research in the summer, living through more and more 100-degree days. And they want to work on it. They want to do research on that topic. And for us, we since we're working with climate model data, it's nice to be able to have sort of like a Ferrari at your fingertips. We can look at so many different types of problems, and the students can really dig their or sink their teeth into problems that they're interested in. But you covered a lot of what our lab works on. We think about river flooding, and we think about hurricanes. We think about extreme rainfall. Mostly, we are looking at the hydrological cycle, the water cycle, but I have had students that work on heat waves and extreme temperatures as well. And of course, these things are connected. Um, but I think the major difference between what I do and what other climate scientists do is that I do bring in this lens of the past. So trying to use the past to inform our future.
So I want to ask maybe one more question about your work before we go to our final lightning round here today. And it might be a question that folks have been thinking about as they've been listening to this interview. We know, and you mentioned 2024 was one of, if not the hottest year on record. And there are obviously lots of discussions about how the U.S. should be engaged in conversations related to climate change, what our role should be in that conversation. And I wonder if you have any thoughts on the best ways for humans to be addressing the changing climate in the years to come. Is there anything in policy or in practice that is top of mind for you as we're increasingly faced with these extreme weather events and other things related to the changing climate?
Yes, if I have one message on this topic, what I tell my undergraduate students is there's some figure about how approximately 100 corporations account for over 70% of emissions globally. And so there's been this effort, I think, within our society to shift the burden of blame onto the individual. Oh, turn your heat down, recycle, et cetera, et cetera. But really, it's 100 corporations that account for 70% of emissions. So for this to get better, we have to not only adapt to the changes, but we have to reduce carbon emissions. And that has to come from either the private sector doing that on its own or from government regulation. You see this working really well in places like the EU. They're certainly restricting the amount of carbon that different companies can emit, and they're putting caps on each country's emissions, for example. And that has caused technological innovation. They've found ways to get the electricity that they need using different sources and looking more towards renewable sources. And so, one thing that's been expanding rapidly, and many people at Rice are working on, is geothermal. There's huge potential to use geothermal energy in the United States that's currently very untapped. Um, Many listeners might not know that Texas is actually the leader in wind production in the United States, and we really kind of triple lap California on how much wind energy we produce. So we have the tools to do this, but there needs to be either incentive coming from policy or there needs to be a push internally from the companies that are responsible for the majority of emissions. And specifically in the United States, right, we know that we are responsible for a lot of global carbon emissions. We are one of the top emitters, and we have been for the last century. And so the burden of reducing emissions has to come from the countries that are emitting the most carbon dioxide. And so we do have a responsibility. Whether or not the current administration is going to take that responsibility on, I am doubtful, unfortunately. But I think that hopefully there are brighter futures ahead.
All right, so I want to shift to our rapid fire questions. These are three questions we've asked every guest this season. And we'll start with the first one, which is tell us about your favorite spot on the Rice campus.
Oh man. Okay. Great question. I love to walk around the loop, the inner loop, the outer loop around Rice's campus. I don't know if this is a good answer, but I actually love the outer loop, the gravel path. I run there a lot. I guess to be more clear, I slowly jog. But I think one of my favorite parts about Rice is the beautiful oak lined gravel path that we have. So nice to walk and take a break or take a little jog.
That's great. I think everybody can picture that in their minds. Really special part of campus. All right, second, what's the best book that you've read recently?
I think my answer to this is going to be a little haunting for some people, but I, I read a really good book about how to fight burnout. It's called Burnout Disrupting the Stress Cycle or something. And it's something that helps. I'm an assistant professor and it's a tough job at times. And so it was a book that I read recently.
Any advice? Any advice that you would give our listeners from the book?
Oh, man. I mean, the book has many chapters, but one of them is just about, exercising to reduce stress. So that certainly helps. But yeah, it's a great book if you're looking to fight burnout. Oh, and working on things that bring you meaning. That was another good piece of it.
That's great. That's great. Awesome. All right. And then our last question. So when students apply to Rice, they are presented with the box, which is a question on the application where they're asked to share an image of something that appeals to them or something about themselves or their interests, something that sort of has meaning to them as someone who's applying to Rice. And I'm curious, what image would you put in your box?
Oof, that's a tough one. I hate to be trite and zero in on my career and everything, but I do. I think I would draw a picture of Earth. Um, I really care about what I do, and I really care about teaching. And one of the great joys of my job is working with the rightest undergrads. And I always start all my. Maybe I would put this phrase in the box. If I know I have to draw something, but instead of drawing something, I might draw a picture of Earth and then put a little quote under it, which would read, "What will you do with your time on Earth?" I think that's what I would put.
Fantastic. Awesome. Well, Sylvia, this conversation has been really interesting. Thanks so much for sharing about the work you're doing, the research you're doing. Obviously, this topic is so top of mind for folks, and really just appreciate the time today and sharing your good thoughts and perspective. Really enjoyed the conversation today.
It's my pleasure. Go Owls. Thank you for having me.